Hello and welcome back to Calculus 1, section 3.6 on derivatives as rate of change. So we are going to look at all of these derivative applications now between either instantaneous and average, and understand which is the appropriate to use in what situation. So our average was given as the slope of the secant line, and that was f of b minus f of a, right? Two values over b minus a. That's good. And instantaneous was the derivative. We call that the tangent line. So slope of the tangent line was the limit h goes to 0 of f of x plus h minus f of x divided by h. So these are the things that we did so far, and now we want to put this in a context of the world around us. So the first talk is the talk on velocity and that stuff. Hopefully you are familiar that your speed, right, is given in miles per hour. Hopefully you are familiar that you are covering miles. And even though you generally count minutes to get here to campus, we still convert those minutes to hours. So if you are traveling 20 minutes, that would be 1/3 of an hour. If you are traveling 12 minutes, that's 1/5 of an hour, or 0.2. So you can easily convert your minutes into hours and have those converted as a decimal, right? So that you can do calculations. Now, the distance you cover from home to get here is going to be given in miles. You convert your time, minutes, into hours, and you can come up with the average velocity. Would anyone like to disclose how far they live and how long it takes them to get here?
It's like 15 miles. I want to say it's like 25 minutes.
15 miles. And you said 25 minutes.
Yeah.
Right.
25.
So now I'm going to say this is 15 miles over 25 minutes times 1/60 hour per minute. Because now when I cancel minute in the numerator and minute in the denominator, we're only left with hours. So this calculation is actually 15 times 60 divided by 25, and then it's miles per hour. And your average velocity would be, this will cancel a 5 and leave a 3, and this will cancel a 5 and leave a 12, 36 miles per hour. So that will be your average velocity to get here. Now we know that you were not going 36 immediately because you were parked, right, to get in a car. You have at least one stop, right? You have at least one stoplight. I mean, stop sign. Oh, you don't stop for that? And then
2, 3, 5, 4, and then turning 5.
So five stop signs at least, right? So that's at least 5 times when your speed was 0. Well, that means that you were going at some cases well over 36 to compensate for that average of 36 down to 0 to make a stop. You're supposed to stop for 3 seconds on the light. So that's the average, right? So now going to understand how do you actually get places, right, using the car? You have 2 pedals, right? If you have more than 2 pedals, then it's time to upgrade for something more efficient, which is 2 pedals.
Yeah, it's miles per gallon.
So you have gas, right? Gas pedal. We call it accelerator as well. So what do? Your car is parked to 0. Then you push that pedal, and that pedal makes the velocity change. And because the velocity is changing from 0 to something, you are able to cover the distance. Observe this now. He was stationary, and now he's moving, right? And because he's moving, he's going to cover the distance from here to the place. So what do we have? We're going to have a position function usually denoted as s of t, because word position has an s in it, clearly. Right? If you call it p of t, it would be very confusing. Then we have velocity function, which is v of t, and then acceleration function. A of t. This is generally what we use. Now I will add also jerk, which is j of t, because that's something that you can also experience in your car. So now you are going to start with a position function of some kind, and then you will keep taking derivatives in respect to time to come up with the next layer of a function. Now, let's think about this. The position function is going to give you how far you go in time, in miles or meters or whatever. So, position function s of t, silly me, right, p of t. So position function s of t is going to give us the distance covered, right? So that's distance covered. Say in miles. Could be meters, could be kilometers, could be inches, whatever. Now, we know that the velocity is going to be the derivative in respect to time. Does this make sense? Well, yeah. Velocity is change of position in time. So change in position and change in time. In order for me to claim I had velocity, I have to change the position, and since I'm not teleporting, right, the time will elapse for me to get to the, let's say, printer over there. So this one over here is velocity, and that one is given in miles per hour. Does the unit make sense? Sure it does. I do see distance for miles divided by time for hours. So miles per hour. That all has to make sense now. Then we get to those pedals in a car that actually make everything move. Acceleration is the change of velocity in time. That one is given in miles per hour squared, but generally we don't use it in those terms with a car. So we'll say gravitation, right? Acceleration of gravity due to gravity of either 9.81 meters per second or 32.2 feet per second. But acceleration is change in velocity. Now think about the two pedals you have. Velocity is going to give rise to your speed. Speed is just the absolute value of velocity. Speed doesn't care of the direction you're moving in, just how fast you're moving. You know, you have speed limit. You don't have velocity limit. You have speed limit because, you know, in our social construct over here, everyone should be sane enough to drive in the same direction, the same lane on 78, right?
No, that's not true.
That's not true. I've seen them. Yeah, I've seen them reverse too. I missed the exit in reverse on 78. Really? Anyway, because there's no next exit. Next exit is in Kansas, so you can't really make the connection. You know, it's 4 days of travel to the next exit, so you make sure you reverse on the highway. Anyway, two pedals. Those two pedals both change your velocity, your speed, right? You push the gas, your velocity changes up. You push brake, velocity changes down. So both of those pedals are acceleration, accelerating and decelerating, but still positive and negative acceleration. And you can see from the formula here, change of velocity in time, right? As you drive by and you see the cop car right hidden in the bushes, can you instantly change the speed to the speed limit? No, right? That's why you pay. So when you look into that, you know, mirror and you see right behind you, right? And you immediately feel safe and protected. Anyway, what, you don't? That's what it says on the car, servant protected. Go get me here. Sorry. Anyway, so we have this concept. So the distance function will tell you how far you go, which is the distance. The velocity is going to be change of that distance in time, miles per hour, looking at the units. And over here, acceleration changes the velocity. And now I'm going to put the jerk as well, because this is what you can experience immediately, which is change of acceleration in time. We have a seat belt, and then you have that little cushion that you can adjust in the car. So that cushion is extremely important, let's say in Tesla, because acceleration of that car is insane. Right, there's a button called to say push the button. That much acceleration pushes your head back, right? Same like getting the rear ended, right? Pushes the head back. So you have that little pillow there, or whatever it's called, right, to protect. But the one that is mostly important, obviously, is the seat belt. Because another type of acceleration is deceleration, which is slamming brakes. Now, does it matter how fast you slam on the brakes? Right? So when you experience a lot of jerk, when you really slam on brakes, right, you go forward. If you push them slowly, right, so change of acceleration or change of time, right? Cops also sometimes give the, because they judge the speed. As you drive by, they have no clue how fast you're driving, but they actually see you braking because your car goes down on the front when it brakes, right? You slam on brakes, the nose sinks a little bit. So they see that. And knowing how much the car sinks, they say, oh, this one is braking a lot. Right, so let's say it was going 95. It's approximate. So you can experience all of these as you drive. And this one is simply how fast you slam on those pedals. Do you press them slowly? Because over time, it's change of acceleration over time. Remember, the amount you press the pedal is the amount you either brake or accelerate. So, if you push this, you floor it, right? You change acceleration. Acceleration changes velocity. Velocity changes distance, and you launch. right? That's the way it goes. So it all starts by you pressing the pedal, which is the J of t. How much of that are you going to exert on the system? And you still owe me the other ones that you already? Nice. So this is the list. Now we're not going to use jerk in the class. We're only going to worry about the position function, velocity function, and acceleration. And then when you go to physics, you will enjoy apparently 6 levels of this. Yeah, 6. So you'll get there. So say that I have the S of t given as e to the 3t plus 4t squared minus 3. I can immediately find other ones by simply taking the derivative. Velocity function would be 3e to the 3t plus 8t, and acceleration function would be 9e to the 3t plus 8. Now I can ask you, how far is the object? At 0 seconds. So for t equals 0, S of 0, which is the initial case that we are considering, would be 1 plus 0 minus 3, so negative 2. Velocity of 0 would be 3 plus 0, which is 8, in whatever units we're using. And A of 0 is going to be, this is 9 plus 8, 17. At t equals to, let's say, 3 seconds. Okay, well, let's say that this is feet per second, and this is feet per second squared. So for t equals 3 seconds, it's going to be S of 3. S of 3 is e to the 9 plus 36, 33. E to the 9 plus 33 feet. Velocity at 3 seconds is going to be 3e to the 9 plus 24. Feet per second. And finally, acceleration at 3 seconds is going to be 9e to the 9 plus 8. And that's feet per second squared. So it's very simple to calculate these things. If you have the position function, you take 2 derivatives, and you got your velocity, you got your acceleration, and you go from there. Now, the reason we do this is obviously to be able to track the objects, right, as they progress or fly or whatever it is, right? You can trace the motion using this. The application here would be one of the original things that Newton did, and that would be parabolic motion. Now I should say in 2D, but the entire Calc 1 and 2, well, some are 3D, but entire Calc 1 is 2D, so whatever, in R2 in 2D. So you have real axis for X and real axis for Y, so you say R squared, that covers those, and then R cubed obviously for 3D because you're adding Z to the mix. So parabolic motion. Are we ready for the experiment, everyone? And go. One more. Ready? This one's going to go higher, right? So what we've seen is progression in time. Now, as you are learning this, we give you the formula for vertical, let's just call it height. There. So S of t, right, or how high the object is, S of t is going to be -1/2 gt squared plus v0 t plus y0. So this is our initial equation. Now you have to take this equation as granted right now, and then in chapter 5 we'll derive it. So what do we do here? Well, first off, we have g, which will be given as 9.81 meters per second squared, or 32.2 feet per second squared. So that's g, depending on your metric or imperial units. Now, can I round this to 10? Sure, depending on how picky you want to be with the problem. Then we have v0. That's initial velocity. Initial velocity. I'll do one more example. Note that both markers that I threw before ended up, well, one is in front of the printer, the other one is closer, right? And the difference is pretty much initial velocity, because I can just do this. It's the same direction which I threw, right? Marker, it's the same marker, same weight, same everything. We have the same gravity. The only difference, and I'm sitting on the same chair, so the only difference between this marker and the other markers over there is how much initial velocity I put into the throw. That's literally how much muscle you put into a throw. Because, see, it goes further if I put more initial velocity. All of the initial velocity for that object is given by my hand throwing it over. So that's what the initial velocity is. And finally, we have y0, initial height. You can throw with the same intensity from higher, it will go further, right? That should be common sense. So you want your basketball players to be tall, right? Because they will be throwing the ball from the higher altitude. It's easier. Now you see that the formula up there, everything you have is necessary and needed. Now, if you are thinking about dimensional analysis, gravity is given, let's say, meters per second squared, and time squared is given in second squared. Second squared and second squared cancel. Velocity is given in meters per second, times a single t is just second, that cancels. And then y0 is given in meters. In physics, this must happen 100% of the time, because on the other side, you have also meters. Meters are equal to meters plus meters plus meters. Right? You can't add units that are not of the same kind. It makes no sense. Right? It makes no sense. So you can't say 5 feet plus 3 newtons, that's one is unit of force, the other one is unit of length. It doesn't work. And as you can see over here, everything works out nicely. All units cancel out. And you have meters is equal to meters plus meters plus meters. Now, how much? That will depend on the values of g, v, and y. Can we change the value of gravity? Yeah, just move from Earth, right? You have less gravity. That's one of the, well, yeah, Mars is the issue, right? Because, yeah, we can make our little cute habitats and stuff like that, but when you think about it, it has poisonous soil. That's the issue. The atmosphere is not breathable either. But you make little huts and things, and you shield yourself from poisonous soil, and you produce your air, and you okay, fine. One thing you can't fix is gravity. Okay, that's a thing you can't fix, because gravity, pull of gravity on Mars is smaller than Earth, because Mars is much smaller than Earth. So if you're experiencing 2/3 of gravity, what's going to happen 5 generations down, right? Yeah, and the bone density, yeah, less muscle, bone density is not going to be there. So they show up on Earth. So, that's it. Really? It's called a pending doom. Pick a time. How about 7:50 p.m. today? No, how about tomorrow? That's the best. You procrastinate like that. There you go. It's the same like you do with homework. See, I do with updates. Okay, I'll update when you hand in the homework. How about that? Hold on, I'm exercising over here. For this week. So that's our equation for the path. I just picked them up. I don't want to throw again. Right? When you throw something in parabolic motion, it doesn't matter what you throw. Obviously, it matters what you throw, because if I throw this homework or class prep, whatever it is, it's not going to go in parabolic motion because of the drag and the shape of this, and right. So it's going to go like a paper. But you know, throw something, anything that it's more concrete, it will exhibit parabolic motion. So now, what's the velocity function? Well, we take the derivative, knowing that g, v, and y are all constants. T is the independent variable. So, why is blue? So velocity function, v of t, is going to be the derivative of s in time, and that is simply negative gt plus v0. Again, this has to make sense when you do unit analysis. So v0 is meters per second. Over here, gravity, meters per second squared times second. So that kills a square, plus another meter per second. Yay, it works. Meter per second is equal to meter per second plus meter per second. Excellent. Now you're looking at this formula and say, oh, I have to memorize that? Well, you probably already know it. Just the question is which way you wrote it in physics. Sometimes you write it as velocity final is equal to velocity initial plus acceleration times time. Acceleration is gravity. Or velocity final minus velocity initial is equal to acceleration times time. You had one of these two forms. And that's exactly this formula. So now we have the formula that velocity in time is equal to negative gt plus v0. So that's another important formula for parabolic motion. And finally, acceleration, well, that's the derivative of velocity, and that's just negative g. So we see that acceleration due to gravity is actually acceleration, which is negative g. Now, that is something that helps us hold the orbit, the gravity, acceleration of gravity, because we are moving, right? The planet is going around the sun, and the moon is going around the earth, and so on. So when you look at this, right, it's elliptical orbit with the sun in one of the focal points, and here's Earth. So elliptical orbit, it's fine, all right, zooms around. This orbit is actually very close to a circle, and the sun is very close to the center But, okay, ellipse is ellipse. Why does the Earth go around? The Earth tangent velocity wants to go this way, but acceleration is pulling in on these vectors. So it just bends and it goes around. Now, there are better explanations, obviously, using the Einstein's theory and so on, that the bend space-time and so on, the mass is the curvature of space-time and so on, which you can picture by putting the elastic sheet. You put a very heavy ball in it, it will create this kind of funnel, and if you toss something on it, it will be in orbit. Eventually it will fall down, but when it slows down because of friction and stuff, there's no friction here. So yeah, that's that. So gravity, acceleration of gravity is what actually keeps the orbit. You can put the satellites up, you have the moon around the planet and all of that kind of stuff. So now, for parabolic motion, we have that a of t is equal to negative g. Good. So now we can calculate stuff with this. I want to take a look at one of the homework examples, let's say. Oh, I didn't talk about max height. I have to talk about that as well. No problem. All right, so now we have these three equations. S of t is equal to negative 1/2 gt squared plus v0 t plus y0. Velocity of t is negative gt plus v0, and acceleration in time is just negative g. Those are the three equations we have. Also, speed is the absolute value of velocity. So if you get negative 3, it's 3. Your speedometer always shows positive values between 0 and whatever you have, whether you're going forward or backwards. So the speed is always a positive value. You going forward could be considered positive, and you going backwards is considered negative velocity, but it's right because your direction has changed. However, the speedometer will always show positive values. And what else we have? And now I would like to discuss first the maximum height before we go into problems. So how do we find maximum height of the object? Well, note that when you throw something, it goes up and then comes back down. Unless you're Elon Musk. Right? It goes up. And actually, half of it comes back, right? Half of it comes back, and it's reusable. All right. So you shoot something with initial velocity v0, and what happens at the top with the velocity? 0. You see, if this is my s, right, distance, the velocity here at this is velocity is equal to 0 because it's derivative. It's the maximum point. And that makes sense, because when the object goes up, we can do this experiment. When the object goes up, it's going to stop, and then it's going to come down. So, right, it stops on the top. At the max height, it stops. So velocity is 0. So initial velocity, which is throw v0 that I give, right, is going to be diminished by the gravitational pull as the object goes up. And when this equals initial velocity I gave, which means it slowed it down, it's going to stop, and then the gravity is going to start pulling down. Your initial velocity in that part of the trip is going to be 0 because the object stopped, and then when gravity starts pulling down, the object is going to start going down. So we have the velocity equal to 0. To find max, so to find max height, set v of t equal to 0 and get time t at which object is at max height. So once you have the object at the max height, you can plug that into s of t to get what is the max height. So plug in to s of t to get max height. Plug what? Plug t that you got into this. Alright, so now you're ready to take a look at the example. There are more formulas for range and angles and things like that. If you're interested, you should look into that. It's really nice. Problem 24 in the new textbook says, suppose a stone is thrown vertically upward from the edge of a cliff on Earth with initial velocity 19.6 meters per second. Earth, cliff, initial velocity of 19.6 meters per second from a height of 24.5 meters, so h0, 24.5 meters above the ground. 24, that's 12 times taller than me. 12 times. All right. Why is it important to say Earth? Gravity. Because again, different gravity constant on Moon. Right? You saw them bounce on a video. Why do they bounce like that? The gravity is... How much effort do you have to use to land or take off of the asteroid? Pretty much nothing, right? There was a NASA competition 2 years ago. Math Club was interested to participate. They had competition for individuals or clubs to design the landing gear for the asteroid. So you were supposed to come up with some kind of landing gear that will take your satellite and land it, attach it to the asteroid. Now that's near zero gravity right there. You technically need toothpicks to do that, because there is no, right, once the satellite is moving the same speed as the asteroid, right, it's not going to experience any, well, there's no drag, there's no wind, none of that stuff. So all you need to do is to just have some anchoring. That's all you need, right? You can shoot in a harpoon or something and just kind of get to it. It's a very interesting project. So Earth means that G we are using is 9.81 meters per second squared. That's why we say Earth. Great. What is my formula? Well, I have S of t, which is -1/2 times 9.81 t squared plus initial velocity of 19.6 t plus initial height of 24.5 meters. See you next week. So now, we simplify this S of t into an equation, negative 4.9 t squared, that's good enough, plus 19.6 t, plus 24.5, and the entire equation is actually in meters. So I'll put meters in brackets so we know what the units are. I have equation. Immediately get velocity function. Velocity in time is going to be negative 9.8 t plus 19.6. That's it. And it's going to be in meters per second. And acceleration in time is negative 9.8 in meters per second, or second squared. So, max height. We calculate V of 0, which is negative 9.8. No, V of 0. V is 0 equals to negative 9.8 times time plus 19.6. So time is going to be 19.6 divided by 9.8. We are going to use 2 decimals in this answer because 1 decimal was given to us in a problem. So we just go an extra decimal. 19.6 divided by 9.8 is 2. I'm not thinking at all. 2 seconds. So 2 seconds after you throw this rock, it's going to take 2 seconds for this rock to reach the maximum height. So now I need to calculate S of 2 to see what is the height. So that's going to be negative 4.9 times 2 squared plus 19.6 times 2 plus 24.5. So S, well, you can say S max height, is going to be negative 4.9 times 4 plus 39.2 plus 24.5, 44.1 meter. And that's it. That's the max height. For your parabolic motion, when you draw this and you have your S over here, this value here for the max height is 44.1 meters. This time t at which it happens is 2 seconds. That's in seconds. And S is going to be in meters. So you can calculate all of these things if you're interested. Now we don't have to use only velocity, acceleration, and that kind of stuff. We can use this for other purposes as well. Growth of population, decay of garbage and radioactive materials, or decay of, I don't know, whatever. Decay loses mass, right? And growth accumulates either money or population. So we can work these things out for population, for instance. So population. We know from our pre-calc that population model is given by population in time is equal to initial population P0 times e to the kt, where this k is the growth constant of population. So this is the formula from pre-calculus. And now, it's very simple for me to actually go and say, change in population in time. In what time? Per day, per month, per year, per decade? We can do that. And you have now simple derivative, which is kp0 e to the kt. It calculates the change of population. So how much new people or fruit fries or whatever you're looking at you add in the interval of time. Now generally what I do is I go to population clock, which is census.gov. And then you see the US population, and you see the world population. So if you look at these numbers, it says components of population change. 1 birth every 8 seconds, 1 death every 12 seconds, 1 international migrant net, this is US statistics, 1 international migrant net every 29 seconds, net gain of 1 person every 13 seconds. So every 13 seconds, at all times in the United States, plus 1. That includes deaths, that includes, right, it's a model, mathematical model. So it's plus 1 every 13 seconds. That means about 5 new people per minute, times 60 per hour, times 24 per day, times 365 per year, and so on. The world, on the other end, China, India, over 1 billion, followed by United States being a quarter of what they have to offer. Going to Indonesia, Brazil, Pakistan, Nigeria, Bangladesh, Russia, and the tiny islands of Japan, but they are closely packed like sardines. So 126 million, how, I have no clue.
Is this the current population or the amount to grow?
Current population, 7 billion and 5.
No, I meant, is that like
These are the current populations, yeah.
I can't see it.
Yeah, July 1st, 2018. So now, what do we do? Well, first off, we know that this model for population is bad, the one that I gave you. Because if you take the limit as time goes to infinity, it tells you that population can go to infinity, and it can't. Because we don't have infinite land, infinite resources, meaning food and fuel and stuff. So you can't have infinitely many people on a surface of the planet that has a finite surface area. It's a ball. It's a ball. All right, good. So, a little bit squished, but. So what do we have? We have different models, right, that do a better job. But on the short run, right, you're looking, a few decades back and forth. This model is going to work. But if you really want to look at for a long time, this model is terrible. You have to use what we call logistics model or some other models that are given, and you will see them when you take differential equations. The entire lecture just on population models. So in chapter 1. So woohoo, right? So now what do we have? We have 2018. Come on, pen. You can do it. Is this the day when none of the batteries are ever going to work? And Alright, come on. I think you ran out of ink.
Is the penny the battery?
Yeah. No. See this little dot there? Just gave the dot. Won't erase it though. What happened? You're good? That's good. Ha! Yes? Okay. So, let's go. We have 2018 for the population of 7.5 billion. Let's go some decades before. Population in what year?
5.
In why 1995? Okay.
Like 1901. 0005. Just 5.
Just 5. Like 580. Just 5.
I said few decades, and you go back 2 centuries. Not 2 centuries. 2 millennia. 2 millennia. 1970, 1970. Since 1970. $3.692. There we go. I missed you.
I told you I didn't trust it.
Now the important part is to say that this is going to be our initial point as 0 for time and 3.692 for population, which would make the upper point to be 48, and then 7 point, we can do better, 523, 524, 525, no, I'm just kidding. All right. I'll add 24 up there. So now, when we use our model, P0 is where the 0 time is. So this is your T0, P0 point. And this is your TP point. So immediately we know that P of T is equal to 3.692 e to the kt, and now we plug in this one to calculate k. So population is 7.524 equal to 3.692 e to the 48k. Divide both sides by 3.692, so 7.524 divided by 3.692 is 2.038, is equal to e to the 48k. ln both sides to get rid of the e. So we have ln of the answer from before. That's 0.7119 is equal to 48k. And finally k is equal to, divide by 48, 0.01483. We keep 3 significant figures. We got k, which is the constant of population growth. So now my mathematical model P of t, this is all pre-calc 1. P of t is 3.692 e to the 0.01483 t. This is what we call mathematical model. Now scientists have something that's called carrying capacity of the planet, which is the maximum number of people that the planet can support. They can't agree about the number. It moves anywhere from 10 billion to 15.2 billion in my research on the proposed numbers. What happens at this carrying capacity of the planet? At the carrying capacity of the planet, all of the resources of the planet are utilized to the maximum, and you can't add more population because simply there is not enough surface area, there's not enough resources, just not enough to sustain more population. Now that's a wide range, and if you paid attention, did anyone notice that we doubled in 50 years? So if we double in the next 50 years, and it goes faster than that, if we double in the next 50 years, we'll be in that range of carrying capacity, right? Because 7.5 plus 7.5, that's 15, right? That's the upper bracket of the carrying capacity in less than 50 years from now. That's the crude estimate. But we can actually check if you want to calculate, because we have a mathematical model, we can guess, right? You can either calculate how long would it take to get to, and you plug in 13 billion, or you plug in 13 billion, right? Or you say, what would be the population in 10 years? You plug in 10, population approximated in 25 years, 25. So when you have a mathematical model, you can either give the years to figure out approximated population at the time, or you can produce, you can say, how long will it take us to reach by this approximation? Let's say 13 billion. And you just run the calculation backwards, and you can calculate the time. So let's say that this 15.2 is the absolute, that's the largest number I've seen. So maybe someone came up with even bigger one, I don't know. So how long will it take us to reach 15.2 billion? Well, you just write the rest of the model and solve it. Divide 15.2 by 3.692 to get 4.117 equal to E 2.01483T. You ln both sides. So now we take the ln of the answer to get 1.4151. I always keep 4 decimals because exponential functions have a lot of error if you round crudely. Equals to 0.01483T. Just do the division. Divided by 0.01483. Say will take, by this model, 95 years. 95.4 years. To reach by using this model, right? What happened? Yes, from 70. So you have to add these 95 years to 1970, So 1970 plus 95 years, that's going to be a 5 and a 6 and a 2. 2065. Right. So better models are introduced later in Calculus 2 for this, and even better models are introduced later in differential equations, which Calc 2 is prerequisite for. So a better model would graph this way. Where you have this horizontal asymptote at carrying capacity K. So you have your initial population. When you start measuring, that's your T0 time, exponential growth, and then it has to smooth out. Now, is this the only thing that behaves this way? No. You can think about decay of garbage or radioactive decay. We have lots of nuclear waste because we can't figure out the fusion yet. It's always 30 years away for last 60 years. And then we have issues of with plastic and all the garbage and all the piles. Decay of radioactive decay of elements, alpha decay, right? Happens all the time for everyone. So all of that stuff is there, but then you can apply it. The way the drug metabolizes in the body, it also has the half-life. So your Advil is 1.9 hours half-life, biological half-life of Advil. So you can find that in Wolfram Alpha or online. So you can run a basic decay problem with Advil or any other medication to see the rate at which it metabolizes in the body. So you can see that if you roughly, you can do rough calculations. You don't have to run calculus for those things. Say you take 400 milligrams, I think that's 2 pills. You wait 2 hours, it becomes 200. You wait another 2 hours, it becomes 100. Because half-life cuts the existing mass in half. So it's not 200 and then 0. No. It's half of, that's how half-life works. Lambda. It cuts the existing mass in half. So 400 milligrams that you took in 2 hours is going to be half of that left in 2 hours, half of this half left, which is 100. It's time for your new dose, right? So you take another 2, and now you're at 500, and then you wait 2 hours for 250, 2 hours, 125. See what happens with each new dose you take? It actually increases. So over time, right, the dose of the medication that you are taking, if you are taking it at exact intervals, right, when you're supposed to, the first time around after 4 hours you had 100, the second time after 4 hours you have 125. Now you're adding another 400 for 525. Cut that in half, goes up again, and it always goes up until you stop taking it. And then, when you stop taking it, and you have no more take, the exponential decay graph kicks in and tells you that the amount of medication that you still have in your system in time will reach 0 when time reaches, there we go, See? You can do these things like that. Beautiful, right? Yeah, you still carry everything you ever took. It's like, you know, minuscule, but you got it. Things work for a long time. So these are the things that you can work on, discover, learn as you go through these exponential decay. Same thing goes for, you know, throw this, right? Plastic. It's a good quality plastic. Takes 16,000 years to lose half of its mass. I actually had students calculate that in a pre-Calculus1 project, right? Because it's something that you can find. The type of plastic used to make this, it was this particular marker that I asked about. So the question for the project is just figure out the mathematics of decay of expo marker. That's it. That's the question. Stuff you're gonna get in different on a calculus pad. So what do? You go and you find out stuff about the marker, and then you just run calculation, and you come up with 16,000 years or whatever, right? And then we know why people want to ban the plastic bottles and stuff, right? So it is a lot, right? Planet's gonna be fine no matter what we throw, because everything's made for the planet, right? Just we are creating a poisonous environment for us to live in. Right? The planet is just a rock. Moon is just fine, right? Don't worry about the polluting the moon, right? Can't even live there, so yeah. So they're not gonna save the planet. We're just saving our environment so we can live in. So be selfish and just recycle and try to use less plastic, I guess. Good. How about some business? I'm gonna do the cost function. "99 of all businesses fail." Why? Well, let's see why. People can't do math, right? But the price for something you make doesn't cover all of your costs. Where's the cost? Everywhere, right? You have the truck, and you have insurance for the truck, and you have to change the tires for the truck, and brakes for the truck, and everything, right? You have to maintain that truck, right? So you can't sell at cost. Also, because you need to collect some profit so you can have an R&D department, research and development, so you can develop, so you can pay engineers and people to develop better products so you're competitive on the market. You can't sell at cost. You have to know what the cost is, right? Now for that you're going to take business classes, and you're going to learn about the variable cost and the fixed cost and how that all plays together. Here in this class we're going to play only with cost function is given. You don't have to come up with one. You will take business courses to figure out how to find the cost function. This problem is concerned is what to do with the cost function. What kind of analysis you can do when you have cost function. So we look at the average cost, and we look at the marginal cost, which is the derivative. But I guess the word marginal is less threatening than derivative, so we use marginal when we do business. So what do we have? We have first cost function. I'm not sure why I'm doing this red, but yeah. Cost function is C of x. Cost function. And then we have average cost. Which is C bar, which is a cost function divided by the number of units you make. And finally, marginal cost is just C prime, the derivative. So these are the three that we are going to look at. Now I really like the problem that it's presented in a book, because it has some really great insight in the cost analysis. So I'm going to steal the function. This is one of the rare times when I actually take the function given in the text, because I know you know all the letters and numbers and you can read it if you're interested. But it has some really good points to maybe 3 or 4 times per course I would take something from there. Generally I like to stick with homework, because you can read what's done. But anyway, cost function given as c of x equal to negative 0.02x squared plus 50x plus 100 for making first 1,000 units. I don't know what you're making. Phone cases, markers, cars, airplanes, whatever you're making. You're making only 1,000. I mean, you're doing cost analysis for first 1,000 units. So we can immediately find the average cost by taking the cost function and dividing it by x, which is negative 0.02x plus 50 plus 100 over x. So that's my average cost. And then I have the derivative, which is the marginal cost, which is negative 0.04x plus 50 it's marginal cost. So that's what I have. Cool. Now I look at the cost analysis, and they're suggesting that we should take a look at 100 units. So x equals 100 units. I'm going to calculate both, and then I will explain the difference between the two. Cost of producing first 100 units. Now average cost per item, right? Is going to be negative 0.02 times 100 plus 50 plus 100 over 100. That's 149. Per item or unit, whatever you want to put. Item, unit, whatever. I put unit before, so I'll put unit again. Per unit produced. So it costs you $49 on average. Now, does it mean that it costs the same to produce each item? The answer is no. What is the very first car that Tesla pushed out? Roadster. How much is that car?
Like 70,000.
More. It was over 100. And then, for the population, it was 170.
Really?
And then he launched it in space, so it can float around Mars. Model S, it's anywhere between $70,000 to $100,000, $105,000, right? The Model X SUV, 140, up to 140,000 to buy Model X. That's the one with the wing doors that open up, right? Why? That's to set up the production. That's to make a factory that's gonna make this stuff, right? It's to make the factory is gonna make the batteries, and factories making motors, and factories gonna make the body and paint it and everything. And then, when all of that stuff is developed and people bought the early adopters and everything like that, now it's time to produce Model 3. It's supposed to be E, but then Ford wanted to sue them because Ford has something with E, so they changed it to 3. Model 3. So now it's just E flipped, exactly. So now that car is going to be the cheapest of all. It's about $40K, right? It's a half of Model S, and it's about a third of Model X in price. You can load features and get it up to 70 if you want to, but at that price you can buy S or Y. So it's not just is making the same. The first units that come out of production, they're extremely expensive because the machine that makes them was pre-purchased, right? Purchased before you started production. You have to have a machine which will produce things. So that means that if you buy the machine to make the marker and you only make one marker and you shut the factory down, this marker is millions of dollars because you have the building and the machines and all the utility and gas and electricity and water and right for bathrooms. You have all of that, maybe workers and all of that stuff. It's very expensive, right? So you are not pushing the first marker yet. You're already out a lot of money. And then you make your first marker. The price of that marker has to cover all of the cost and make the profit to start developing new and better marker. You need a profit as well. Then you make another marker. Now it's half, I don't know, let's say it was $1 million to set everything up. So now each of these is $500,000. And here, each marker is $250,000, right? How many markers do they have to produce since they're selling them for 25 cents each, right? You understand how much they actually make of these. So you can't look at average cost. You also have to look at the marginal cost so that you know how much the particular unit costs. So when I look for C prime of 100, I'm looking to find the price of the 100th unit. 100th unit. So nothing to do with 99th, 98th, or 57th, or 34th, nothing. It's exactly the cost to make that 100th marker. So 96, 97, 97, 98, 99, 100. The price for this one. That's what I'm looking for now. Just exact one marker. And that's going to be plug in a derivative. -4 plus 50. 46 per unit. In my business analysis, that's good. Right? 49 on average. The 100th one is cheaper. Imagine if this was 50. What does that mean? The more you make, the more expenses you have. You have bad machines that break all the time, a lot of cost to maintain. You have to hire people, you have to constantly. They shut down the mulch factory next to Flemington because of that. And they shut down the recycling factory as well. Because the cost of maintaining that equipment was absolutely insane. They couldn't make it, they couldn't break even, right? With all the stuff that they were selling. So they shut down the whole factory because of that in Flemington, right? And I know people that have been relocated, right? So you need to make sure that this number, when you calculate 100, is smaller. Because that means that the more you're producing, it costs less. And then you go, and the book is asking us to do as well, calculate at 900. C bar at 900. Negative 0.02 times 900 plus 50 plus 100 over 900. So that's negative 18 plus 50 plus, and this is 11 cents. That's gonna add a lot. So this is 32.11 cents. And then we calculate our marginal to see how much the 900th unit costs, and that's negative 0. That's 36, so negative 36 plus 50 is equal to $14 per unit. Great! It's exactly what I want to see when I have a production set up. Because if I'm making 900 units, the 900th unit is only 14 bucks to make. So the more I make, the less cost goes per unit. You can also see here the average. The average cost for 900 units is 32 bucks. It used to be 49 bucks. That's a drop of $17 per unit. $17 per unit is not little. If you are producing 100,000 units or 1,000,000 units, pencils and pens and stuff, right? You make million, right? And then, so that's the business analysis. We are using the derivative to see how much a single unit costs, and we're using average to see. So that's the slope of the secant line on average, and the slope of the tangent line on the margin. There are other examples in the book that you can look at. I think they also have elasticity and stuff, elasticity and economics. You can look at that as well. A lot of other cool things. And then homework on page 186. Oh, did I skip that? I did, right? Oh, wow. There was no calculus. No one said anything. When I did population, did we do any calculus?
No, I was just waiting for it to eventually happen.
Yeah. We're supposed to take the derivative of our model. We're supposed to take the derivative of our model and see how many people we added in a year, so and so. That's what we were supposed to do. We used calculus. We didn't do any of that stuff. So now we have to go back to population, back to time, and fix that. Back to population. So I had a model. Did I remember this? Is this correct?
Yeah.
Yes? Can't remember my daughter's birthday, but this is like not issue at all. I did random numbers. I can't, for the life of me, I can't know if it's June 2nd or July 2nd. She's been around for 4 years. I can't figure it out. But like this one, it's not a problem. So, yeah. We have the model for population for the planet Earth. And now we know that t equals 0 for 1970. So we can calculate now the derivative and then use that derivative to calculate how many more people we add in a single year when you use t equal and then you put some number which would add to 1970. So we first find the derivative p prime of t, and that's going to be 3692 times 0.01483 times e to the 0.01483t. We multiply these two numbers, keep few decimals around. We get our derivative p prime of t to be 0.05455, it's fine. E 0.01483 p. This math model to calculate change in population for a given year. And that is now, which year should we look at? By the way, with 005 it disqualified. Which year we should look at? 2005, okay. So you still prevail in some sense. How many people did we add in 2005? Well, that's t equals 35, because it's 35 years after 1970 and our model is centered at 1970. So population added in 2005 is going to be 0.055 e to the 0.01483 times 35. All right. So times e raised to, no coughing, open parenthesis, 0.01483 times 35. We added 0.092 billion people. How much is that? How much is 0.092 billion? 92 million. This is worldwide. In 2005. You can calculate how many. If you put 49, you will calculate the approximate amount that will be added next year, right, throughout the entire year, because this function is discrete in terms of years, right? You click one and it gives you for that. So that's a derivative as rate of change. You have to understand that the derivative is dy over dx. It's change of y over change in x. For most part today, we add change in x to be time, or velocity and population. But you can also have it to be units like we had over there. So we took the derivative in respect to number of units. For cost function, it was in respect to x, and x is number of units. So we know that f prime of x can be written as df over dx, and that over there is a rate of change. We also know that we have the average rate of change, which is the secant line, and instantaneous rate of change, which is the tangent line. Those work together. We'll have much more of this in our last lecture of chapter 3, related rates. That's all word problems. We'll do a lot with rates called the related rates. So you will have a formula that relates at least 2 or more derivatives in the formula, and one project problem will reflect that. It's a very important concept, so there will be some emphasis on that in class, and we'll see more of these rates as we go. Now, before we go, next class is extremely important. Next class we are going to learn the chain rule. Over 90% of derivatives you will ever take in all walks of education are going to be chain rule, because you don't run into x squared as much as you would wish. You don't run to x squared almost at all, but you are going to run into combination of the product rule and chain rule and stuff like that. For instance, if you bounce a ball, it's gonna stop making hops, and each one next hop will be smaller and smaller and smaller. Or if you put a pendulum and you swing the pendulum, right, it's going to move and then eventually it's going to stop. So it's going to look like that, and then it stops. The equation for something like that is going to be y equals e to the negative at times cosine bt. It's a product rule of two chain rules. Chain rule is the way to take the derivative when you have function composition. One function plugged into another function. Review function composition so that you are able to understand what happens when you take the derivative of it. Otherwise, it's going to be very confusing. You have to be able to decompose the function like this, meaning, and this is again next class, so I'm giving you heads up, you have 2 days to review. If you have f of x given as 3 cosine squared x to the 5, you have to say that you have three functions there. There is this layer. This square is a very tricky business on trig function. I'll just put it aside. Cosine squared x is the same as cosine x everything squared. Cosine x squared is simply cosine of x times x. Two different things. Two very different things. And you will get the same for ln. I'm hoping you're writing this down, because the amount of mistakes happening because of the sloppy notation is absolutely amazing. Thank you. They're taking pictures. So now when you look at this, you know that this cosine has the square that it's on everything. So this function actually, when looked at from far away, is actually x squared function. So you have layers. First layer, second layer, third layer. So what's inner function? X to the 5. What's that in? It's in cosine x. And what's that in? It's in x squared. Well, 3x squared. So now, when you do function composition, and this is the stuff you're reviewing, because we are going to take derivative of this, right? When you look at this plugs in here, replaces this x with x to the 5, and then this cosine x goes inside of this x and replaces x, and becomes squared and times 3. It's not the function composition that you need to know. It's the function decomposition. And the only way to know function decomposition is if you know function composition to begin with. So you have 2 days. Hunt this down on YouTube. Obviously, if you have pre-calculus book, your textbook in chapter 1 has a review of these things. And as I said, more than 90% of your derivatives from next class lecture till the end of your educational career are going to be chain rule derivatives. So make sure you are learning chain rule properly. Then we will eventually get to integration, and we'll learn the most important integration technique called use substitution, and that's backward chain rule. I know, right? So review that. It's 8:20, right?
No, it's 7.
Wow, no one said anything. I was about to go to 8:20. All right?
It's a good thing I backed up. Didn't notice until I did it.
Bye.
Bye.